Hi, I'm Domenico Stragliotto, a solution architect at Xextras.
Hi, I'm Davide Baldo, solution architect at Xextras.
The product we've built, Carbonio Community Edition, is an open source email and collaboration software aimed at companies and enterprises that needs a private and secure workspace. Before talking about how we built Carbonio, I must do an introduction about why we had to build it the way we did, and the challenges we faced along the road. The driving forces of our decisions are our customers and the requirements and limitations they impose on us. There is a lot of need for data protection and data sovereignty because several organizations manage sensitive data and want total control over it. This translates into two main strong points to keep in mind. They want to have total control and liberty of choice on where the data is stored, and said data must not go through public networks or servers. Since our customer base is really varied and its size scales from hundreds of users up to millions, we had to develop a solution that can work and scale with very different installations. For this reason, we wanted to build a private product, one that customers can work with without having to rely on outside sources. And we decided to do this in a world that is moving every day more towards the software as a service model, where data is in the cloud and decentralized. But that is not an acceptable scenario for all use cases, and those are the cases we had to cover. Public sector, military, internet service providers are just some of the scenarios that impose those strict requirements, in which products must remain contained inside a customer network, be it self-hosted or on a private cloud. The big problem is that even if it's self-hosted, they want the same level of availability, security and monitoring that they could have found on a managed cloud solution. With all those limitations, we tried to go for a solution that is strong and well known, that would allow us to start on a solid ground to build on top of. We analyzed the Kubernetes route, but we quickly saw it was not a way that we could use. Our customers are using varied virtualization systems or private cloud services that don't blend well together. Building a solution that could work on all of them proved to give too much problems. We quickly understood that we must give companies freedom on how they want to deploy the product. Since we are not managing their infrastructure, we must create puzzle pieces that can be installed on the company's one, and that can communicate between each other without needing to rely on a specific infrastructure. This is even more true given that we must support installations that go from one server to hundreds without knowing their topology. After seeing all that, we understood that we could no more go on with a single monolith if we had to satisfy all these needs. We needed to switch to a different approach, and that posed yet another challenge on how to do that. Since a lot of the tooling available right now in the market is tuned toward SaaS development, this makes a lot harder for us to find the right ones, but we found a way. Davide will talk now about how we change our architecture to manage that.
Thank you, Domenico. On the old architecture, we were using stateful multi-server pattern. This offered nice performance peaks, but suffered downtime whenever one of the servers was unavailable, since all the data on it was unreachable. Also, if a request had to return data which was on multiple servers, the backend had to find where it was collected and merge it, summing up latency and possible failures. In order to move away from such a situation, we had to remove the state from the instance and centralize it. We relied on Postgre for most use cases, OpenAPI for new schema definition and code generation, and some caching with Redis. We planned a possible migration for every single piece of software we had, creating over 20 new components. To extrapolate services from the old architecture, we devised a pattern. We started from the most user-oriented services and we enumerated every dependency. For each dependency, we exposed the needed data from the monolith itself, creating a new API via a new OpenAPI schema, generating the controller and then linking them to the old monolith classes, even if everything was still running on the same instance. This way, we had the API serving the data needed by the service we were removing out of the monolith. We could then modify the service, making it use the new API instead of directly accessing the monolith classes to make it totally standalone. Once the user-oriented service is fully detached from the monolith and made independent, we could then repeat the process on a dependency and move them away from the monoliths one by one. In order to split the monolith, we needed a way to keep track of every service in the infrastructure. Let me frame the context a bit. We started from the most standard environment possible, CentOS or Ubuntu. You install a package from the repository. As soon as it is installed, you expect it to run out of the box. No big deal. Now take the same example, except now you want to install the package in any host of your infrastructure and expect it to be automatically coordinated with the rest of your infrastructure and start to serve a request right away without any orchestrator or added complexity. That was our goal. For our needs, we chose Consul, which is a service discover on steroid. It provides fast service registration, health checks, automatic exclusion of broken instance, dynamic configuration generation, events, key value for the system configuration, and dark coffee. Once we set up, we found out pretty soon that a complete setup was complex and time-consuming, and the required expertise was outside the field of our typical administrator. We wanted a simple, seamless installation process. What we didn't really want was to force the administrator to study every technology we were using. The only way forward was to fully automate the configuration, and so we did. We only required the bind address and a new password. With this, we managed to automate the setup with the most hardened configuration possible, paving the way for the new security model we had in mind. Now I'm going to show you how we implemented the service discover setup. So first of all, we implemented two variants of the service discover server and service discover agent. So the service discover server has to be installed at least once inside the infrastructure. So if you need high availability, you install multiple instances, and the server is where the console data is actually stored. Every other node, instead, you must install the agent. So from the application point of view, agent or server is the same, so you just need one of them installed on your local system. In this case, this infrastructure is a single node, so I'm just going to install the service discover server. So install. So once it's installed, just say, hey, run a service discover setup wizard, and this is exactly what we are going to do. So first it asks the bind address where the console is going to listen to. So we just specify the only address available. And now it asks to create a cluster credential password. So this is the password we are going to specify whenever we upgrade a package. So I'm just going to specify a password here. And then it starts generating the certificates, the random keys, and whatnot. So now it has completely set up everything. So if I go to the service discover, you can see that the service is up and running. I can use the service discover command to configure it a little bit and to extract the bootstrap token if I really need to. So, for example, here I need to specify the password to extract the bootstrap token. And right now I'm going to install a toy project which we used as pathfinder on how we should set up packages. So we have an image generator and a random generator. The image generator API just returns an image generated using the random generator. Once the setup is done, I can just launch the pending setups. I can insert the cluster credential password, say execute all configuration, and it automatically runs every console-related activity and completes the setup, declaring the intention to access the random generator. And once I install the random generator, the same happens. So I install it, pending setups, and this script, this pending setups script, keeps a list of every package that needs to be run with this post install kind of stuff, so the administrator can keep their sanity. So I can see once I enter the password, I can just launch every pending script, and right now everything is ready. So I can just, for example, random generator. So I have the activity and the sidecar both running. And here we have our token. We just take it and bring on the interface. So we can just log in with the token. And here you can see that you can have full access. And you can see dependencies. And if I take, if I bring down one service, systemctl, stop random generator, for example, here you can see that the image generator is failing because the random generator is failing. And this health check is directly implemented by the service discover. And if you don't have any live instance of a dependency, it fails. Another thing, you can see that in here you have the intention automatically generated for the image generator to access the random generator. So it's an application aware intention, and we specified up to the specific path what it's allowed to call and what is not allowed to call. And that's pretty much it for the simple demo. What we wanted to achieve was full isolation and minimal privileges across services. To reach this point, we created dedicated users, policies, databases, IP addresses. Everything is connected only via the fully encrypted service mesh coordinated by console. Service mesh is usually a prerogative of Kubernetes. It allows to connect every node to each other only through a proxy called sidecar, which enables you to have an application-level firewall and to automate internal HTTPS encryption. Even if an attacker gets access to the LAN, he won't be able to access servers directly. He will be limited to public ports. If a service get compromised with a remote execution, the attacker will be able to access only that service dependencies. We managed to achieve this level of security by encrypting the root console token inside a PGP archive. When a package is upgraded, the password is required to complete the configuration process. Without the password to decode the token, you cannot update service mesh permission and continue your attack. As we mentioned before, our user range is huge, and using standard solution for every database size is simply not possible. It's either too limited for big customers or too complex or expensive for small ones. The usual solution would be to implement a compatibility layer to support multiple databases, but it takes a lot of time and it's really painful to validate every build against every supported database. We wanted a simple solution which still allows a good amount of flexibility for our customers. Luckily for us, many databases implemented the Postgre binary protocol. We currently aim to support Postgre and CockroachDB. Postgre, for simple infrastructure, can scale reads and provide a failover, and CockroachDB for huge infrastructure, scaling both read and write with a small performance penalty. We also support custom deployment, whether directly managed by the system administrator or by the service provider. Domenico will now talk about privacy for files.
Thank you, Davide. To satisfy the needs for a private content management system, we developed a service called Files that is dedicated to the storage, management and sharing of files. The goal of this service is to serve as an internal files management and give users total control on how to access on its contents. For this, we developed more ways for users to give access to them. With direct sharing, a user can give direct access to one or more of its contents inside the files interface, selecting the permissions with which the share is created. The user will still always be the owner of the content with total rights on them. The shared contents will appear in a specific area of the files interface for the users for which I share them. Private links are a facility to access shared contents. There are hard links to a content that can be accessed only by the owner or by a user with which the content was shared. An anonymous user or one which does not have view rights will be unable to see them. Public links are used to share contents via a public URL accessible everywhere. When creating a public link, an ID specific to this link will be created, and the content will be accessible from everywhere. The owner can add an expiration date or even directly remove the link. The URL will immediately no more give access to the content. While we managed to solve most of the problems we encountered, some are still in the work, and we don't have yet a clear and defined solution for them. The first one is about indexing and data search. We studied different solutions, but could not come to choose one yet for different reasons. Elasticsearch is resource intensive and it would increase the cost of installation for customers. OpenSearch is still too new and fast evolving, and also missing some features we think are necessary, frozen indexes for example. Weaviate is still new, and we need more scaling data to be sure it could fit our architecture. Also, we are not sure its model is a perfect fit for our needs. On another topic, we are still investigating on how to fully isolate each process ports and making them communicate in smaller installations where multiple services are installed together. Still to come to a close on which the best partner could be. We are evaluating various ways combined like Unix sockets, G-groups, SA Linux and more.
To sum it up, making self-host products is becoming harder over time. Often the market does not have defined solution or tools for this kind of products. We have to create them for our needs and sometimes partially reinventing the wheel to make it fit our scenario. In a world moving toward decentralized data management, people still want privacy and ownership of their data, and this need will only increase in the future. Looking around us, we feel the need for the rise of a new community, focused on on-premises software. But hey, we are here now.
Okay, so now we should be live for the Q&A session. So thanks a lot for this talk, for this presentation. Now, if you have any question in the chat, so we already have one. Don't hesitate to write them down, and we will try to answer them. And so I'm gonna let you handle the first one. And so I'm gonna let you handle the first one.
So the first one is, what about Solar Cloud? Is that not an alternative to Elasticsearch? Yes, Solar is an alternative, a viable alternative. The only drawback is that maintenance is quite high compared to other solutions such as Elastic. And a normal administrator, system administrator, does not have enough knowledge or time to invest in maintaining such a deployment.
Yeah, well, just to add that since, as we said, we have to handle clients with different size, with a lot of different sizes. Not all can afford a system administrator that manages full time something like Solar or even other tools that we tried, but we saw that were too much complex for a normal administrator to manage. So we have to always choose a solution that could be easy used for even smaller companies installations, and that could be out of the box. So we cannot also always choose the best solution, because sometimes it's not the right solution for use cases.
So the second question is, what are the benefits to use Consul over Kubernetes? So Kubernetes would be a full-fledged solution to handle every service deployment we could have. Unfortunately, there is the same issue. Deploying a Kubernetes is not an easy task and is usually done by service provider. But if you are aiming at providing our software to a simple company that it's not an IT company, it won't be able to manage its own Kubernetes cluster. And using Consul make it more way easier because it's a simple application. You can just install it, configure it. You don't need to study Kubernetes and deploy different backends, storage cluster, and so on. Then we have a third question. Would something like PG Ronga work for search? I honestly don't know it. We didn't check it out. We did consider using Postgre as a search platform, but Postgre full text search is limited to the official Postgre implementation. Usually other Postgre compatible databases do not provide the same API compatibility for the search, for the full text search. So if we do choose to use the Postgres search, we won't be able to use something like a CrocusDB or other implementations. So it is a solution, but it will bind us to the official simple implementation of Postgres. Like a corporate.
Yeah, we're still anyway investigating even the solution we have mentioned, and we're still investigating them because they are fast evolving, like Weaviate or OpenSearch. OpenSearch was not a study solution because what we talk about frozen indexes, but we think that as soon as we as they are implemented, we will evaluate them a lot because it seems one of the most promising solutions at the moment.
So the next question is, can console be used by Russian user because we have problem with access to cloud services? Console is installed on your own node. We are not using any service, any third-party service. So it's just your server. You don't need internet connection at all. You can just run your node, your cluster inside your own private LAN.
Yeah, that's basically the aim of all the software we're developing, that it can be used even offline, and there's no connection to software service companies because we have the restricted requirements of privacy and data sovereignty. So everything we talk about will be installed on the node inside your network.